Okay. Till now we have taken 1D and 2D problems, and the procedure for 3D. Okay. So the note is the procedure of solving 1D and 2D unsteady and steady heat conduction problems. And in general, any problem can be extended to 3D problems. Okay. So you will have some additional terms as we used to get in second coordinate direction or third coordinate direction. So say for example you have del 2t del x2 plus del 2t del y2 plus del 2t del z. So in this case, you can use central in space, central in space, and central in space, and everything, all this will be then coming as n plus 1 and all at I. Okay. And then you can calculate Ri for interior points, and you, AI, AII. Now, in this case, it will be AII, II, you can say RIII, interior points, or IJK, IJK indexing, you can say. Uh, okay. And then you can calculate T nu. T nu is equals to T nu, T old plus omega Rij, AII. Similarly, boundary points. And you can extend the same algorithm. While calculating Rijk, you will have these terms also, discretized terms of del 2t by del z. Okay, it means that you are considering a three-dimensional problem. Suppose this is in 2D, if it is a rectangle, now in this case, it may be a rectangular box like this. It can be a rectangular box of this nature. And it can be, you can say this is X, Y, and Z, and corresponding indexes can be I, J, and K. Now here you can use for loop. So first you can make K loop, then you can make for J loop, and then you can make for I loop. It means that for K, first K constant, J will vary, and with first J constant, I completely varies. So your first for fixed K and J, your first for fixed K and various J's, you are varying I like that. So this small change you will have to do in your code. With this, you can calculate using Gauss-Seidel method. Okay, same Gauss-Seidel successive relaxation method can be used to solve all these problems. Okay. Now, till now, we were discussing about Cartesian coordinates. Now let us, mm, till now we are discussing about Cartesian coordinate. Okay. However, there can be other coordinates involved, and these problems can be, in general, suppose can be solved by transformation. Okay, in general, in finite difference method or finite volume method, in finite difference method, basically, so in finite difference method, some domains transformation is used. In finite volume method, you need not to solve the equations in Cartesian coordinate. Okay. Even if you have I mean, a cylindrical coordinate, for example, then you need not to, because you have already a discrete domain and this is a finite volume. Okay. And volume can be of any type. So this is unstructured or any volume. So any volume can be dealt, and that if you calculate this area and volumes properly, then you can simply use the Cartesian coordinate equations and solve the cylindrical or spherical coordinate problems. Okay. Suppose you are using finite difference method, then you can transform this domain. Now x and y, this can be transformed into zeta and eta. Okay, I mean xi and eta, then that transformation will be such that you get the Cartesian coordinates. So the equations in x and y will be, or I mean r and theta can be converted into xi and eta coordinates, such a way that you get a rectangular coordinate system, Cartesian coordinate system, and then you can solve the problem. Okay. So suppose there is a non-specific spherical coordinate, but a complicated domain. In that category also, such a kind of problems will be converted into a solvable problems with uniform gridding or like non-uniform gridding with structured mesh. Okay. So that is also possible in finite difference method. Finite volume method, you do not need to this is only for finite difference method. In finite volume method, you need not to. So Cartesian or cylindrical or spherical, they remains, or Cartesian, they remains Cartesian. Okay. So this difference, if you understand, then no need to follow any other coordinate system kind of thing. But to do this, you need little advanced features of, to do this, to do this, you need little advanced course in CFT. Okay. So what I'm going to do over here is, we are going to solve the cylindrical coordinate equations. Okay. Rather than solving Cartesian coordinate equation, we will solve cylindrical coordinate equation for heat transfer in a cylinder, for example. We will use spherical coordinate equation for the case of heat transfer in a sphere. In this course, we shall use cylindrical the governing equations in cylindrical coordinate to solve heat transfer problems, heat transfer problems in a cylinder. Similarly, we will use the governing equations in spherical coordinate to solve heat transfer problems or heat transfer in a sphere. That is, I think, transfer in a sphere. Okay, so that's a methodology we are going to follow, and the methods remain same. Okay, method of solution or algorithm, or you can say the mm, you know implicit and explicit method formulation remains same. However, there are some typical features comes into picture when we want to solve cylindrical coordinate system equations and spherical coordinate equations. Uh, So, and that also might be one of the reason that if you use methods for different spherical coordinates, then you will have to be very careful in your programming. So to make a generalized program, people do not go for cylindrical or this coordinate, and then just they use with that, and okay, and that is appropriate, okay, and profitable also. Okay, so first we will go for cylindrical geometry. Okay. So in cylindrical geometries, you can have the 1D problem, and in 1D case, you may be having in 1D case only variation in R direction. Okay. So suppose you have this cylinder. Uh, so what is possibility is that you may have only variation in R direction, or it may be a 2D problem and you may have a variation R or either in Z direction or in theta direction. Okay. So maybe R theta variation or maybe RG variation, or other combination is also possible. Maybe Z theta combination, theta Z combination is also possible, isn't it? It depends upon the problem we have and how we can convert that problem into a 2D problem. Okay. So if there is no variation in Z direction, so this R theta means that no variations in the solution variables in Z direction. Okay. RG means no variation in theta direction. In theta direction. And if it is also possible that there is no variation in, you know, R direction and only variation in theta and G, you can also talk about that problem. Most of the time, you will have very often you will come across with very often you will come across with R theta system. Okay. If you 3D, then it is very easy. R theta z, all coordinate equation has to be solved, and we can make our life easy. Okay. Now, since very often you get come across with R theta system, we will consider now the R theta system, R theta coordinates. Okay. And we will see heat transfer problem in R theta coordinates. So let the governing equation in R theta coordinate. What is the governing equation in R theta coordinate? Uh, okay, let us first talk about 1D problem. Let us talk about 1D problem, this 1D, R problem. Let us talk about R coordinates. Okay. So what is the governing equation in R coordinate? If you refer your first class, then you come to know that del 2 and del R square, okay, plus there will be a 1 by R term, extra term will come into picture del T del R. This is a 1D, one dimensional in a radial direction, one dimensional flow in a radial direction. Okay. So suppose you have this central node and you have this some variation in R, and say this is your R direction. So this is your R direction. Okay. And here you will be having 1D problem in radial direction. So this is R direction, and you have converted this, you have to convert this into various nodes. You have to convert this one dimension, R dimension, into different node. So say this is I, and this is I plus 1 index, and this is I minus 1, this is boundary point, this is boundary point. Okay. This is a center. Center. Let me write this somewhere here. This is the center of, so we are considering this region. Okay, this particular strip we are considering, and any point that is nothing but it is at R distance, Ri. Okay, and the difference between these two you can say is delta R. Okay. Now at the center, if you extend this line, here, then what do you see? Whatever is varying in this direction, it should also be similarly varying in this direction, isn't it? Because it is the R variation only. So whatever is happening here, there is no theta variation. So with theta, there is no change. What do you mean by 1D in R? There is no no theta variation, no theta variations in the solution variable. Okay, theta direction variable. There is no g direction variation. Okay, it means that neither it is varying in this direction nor in theta direction. It means that whatever values at any r, that should be they will also be same here. If you take this same line here, it will be same values. Here also these will be same values. Here also these will be same values. So what boundary condition should be specified here? So if you see, if I'm having value here, it should be the same value here. So appropriate boundary condition is del t del r is equals to 0 at this center. And here on the surface, this is a surface, this is a surface. On surface, it can be some temperature may be specified, and it can be insulated also. It can be insulated, that is also possible, or some heat flux may also be specified in the in that direction. Okay, so it is possible that some heat flux also may be specified. So what do I mean to say is that you can have a Dirichlet boundary condition, you can have a Neumann boundary condition, or you can also have third boundary condition, Robin boundary condition on the surface. Okay. So here at r is equals to 0, it is called as symmetry boundary condition. This is the this is the symmetry condition. This is the symmetry condition. Symmetry condition. Symmetry condition. And these problems are called as axisymmetric problems. Okay. And axisymmetric means there is no variation in theta and g. Condition for axisymmetric. In other coordinate system, it may not be a possibility. That also you have to remember. Okay, only in axisymmetric case, this is likely to be a proper condition at say r is equals to 0. Okay, so you understand that. Now if I have to write boundary conditions, there is no initial condition needed because it's not unsteady. If it is unsteady, here there will be one term and you can solve the problem similarly as you are going to solve this steady problem. Okay, using false transient approach, or you can solve unsteady problem. So let us first talk very simple case, this one. For this boundary condition at r is equals to 0, del t del r is equals to 0, and at r is equals to capital R, you can have t is equals to, you can have t specified, means Dirichlet boundary condition, Dirichlet boundary condition, you can have Neumann boundary condition, or you can have Robin's boundary conditions. Robin's boundary condition. Okay, so we'll consider one case at appropriate time and we'll go ahead. So what my equation should be for interior points? So for interior points, what are the interior points? These are the interior points. Not only three, there can be many. Okay, but we are representing generally I plus 1, I minus 1 before that, after that, or you can have I plus 2 also, I minus 2 also. So interior points, for interior points, so interior point, suppose it is starting from 1 and ending to n plus 1, and this is our point n plus 1. Then interior points are varying from 2 to n minus 1, n minus n, 2 to n, sorry. So interior points, so for I is equals to 2 to n, we write this discretization. So what is the discretization you will use for this term? What is the discretization method you will use? Finite difference method, which okay. So I want to do at I discretization. So I will use central in space. Let's say central in space method for both. So what is the expression for central in space? So if I write this in central in space, then I might get T I plus 1 minus 2Ti plus Ti minus 1, isn't it? Delta R square. Okay. And all are at n plus 1, n plus 1, n plus 1. All are at n plus 1. Okay. You can have a explicit formulation also, and you can use Gauss-Seidel to solve, but we will use mostly implicit method and we'll go ahead. So I'm writing everything in n plus 1. Now, what about this 1 by r? So, r is calculated at ith point. So, we'll say ri, whatever the radius at ith point, that ri. And then del t del r, how do you use del t del r? Central difference. Central difference method for del t del r is ti plus 1 minus ti minus 1 divided by twice delta r. Okay, twice delta r. Twice delta r is equals to 0. Now, what will you do? You will bring these similar terms over here. So, 1 by delta r square, 1 by delta r square plus 1 by 2 ri delta r. Okay. So, this is a coefficient of t I plus 1 n plus 1 minus 2 by delta r square is a coefficient of 2 by delta r square is a coefficient of ti n plus 1. Similarly, you have 1 by delta r square minus 1 by 2 ri delta r is a coefficient of t I minus 1 n plus 1 equals to 0. Now, for this interior points, you can calculate Ri. Ri can be calculated simply by taking left hand side minus right hand side. So, left hand side is right hand side minus left hand side. So, right hand side is 0, left hand side will go here. So, this term 1 by delta r square will come here plus 1 by 2 Ri delta r is here, I plus 1, and you can write n plus 1, minus will become plus 2 delta r square ti n plus 1 minus 1 by delta r square minus 1 by 2 ri delta r t ti minus 1 n plus 1 equal, not equal. Okay, now this is Ri, and then we also need to find out central coefficient. What is the central coefficient? Minus 2 delta r square. Okay, now you know Ri and Ai, you can calculate T nu. Okay, so for interior points, Ri and Ai are calculated like that. Now let us consider the boundary points. So you see the procedure is exactly same, but now the for boundary conditions, now this is a danger. Now this is a danger. Here comes some problem. Okay. However, at r is equals to capital R means at surface, means at surface of the cylinder, at surface of the cylinder. Okay, it can be Dirichlet boundary condition, Neumann boundary condition, or Robbins boundary condition. Okay, so say we have say we have uh, T is equals to T naught is specified. So this boundary condition will become T, and what is the index at? So it means that at I is equals to n plus 1, T n plus 1, sorry, T n, and we are taking what index? N minus n, right? Uh, okay. So we took it like n plus 1 and to n. Okay. And we'll say Tn plus 1. Tn plus 1 is equals to this T naught is a specified value, known. Okay. This is a known value. So this will simply become like this, and then Rn plus 1, Rn plus 1 will become right hand side minus left hand side, Tn plus 1, n plus small n plus 1, and A n plus 1 will become equals to 1, that is the coefficient of this point under consideration. Similarly, you can go for another boundary conditions and you can calculate R and A at surface. Now the problem is with at R is equals to 0. Okay, at R is equals to 0. Now our governing equation is del 2t del R square plus 1 by R del T del R is equals to 0. Now at R is equals to 0, this term at R is equals to 0, this term becomes 1 by 0. Okay, this becomes 1 by 0. So at R is equals to 0, the governing equation is not satisfying. This becomes 1 by 0 and this becomes infinity, and this term becomes trouble. Okay, so uh, how to alleviate this problem? Okay, so therefore we need a special condition. Therefore we need a special treatment. Therefore we need. Therefore we need. We need a special treatment. Special treatment. Treatment to handle this problem. Such a kind of problems did not appear in Cartesian coordinate. Cartesian coordinate was very nice, but in cylindrical and Cartesian in cylindrical and spherical coordinates, you may come across with such situations which are not physically possible. So you have to use some method. Now, a special treatment, this special treatment is called as applying L'Hospital rule. Okay, L'Hospital rule. L'Hospital rule. Okay. Now I'll tell you one thing. Just need not to tell, but many students they may be pronouncing this as L hospital. Okay, but the pronunciation L and H, there is no actually gap between L and H. It is the way they write their name. Okay, L'Hospital. So the pronunciation is L'Hospital rule. What is this L'Hospital rule is? Like suppose you have a limit and your R, okay, So that if limit and you have some x is tending towards capital A, uh, and that function fx uh, is equals to limit x tending to uh, A and another function gx that is also 0 uh, and limit x tending to A g prime x f prime x is equals to some value that is limit, then 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 this rule says that, then according to this rule, then you can write limit x tends to A g of x function and f of x equals to the L. What it means that it it simply means that limit x tends to A gx fx can be written as limit x tends to A g prime of x and f prime of x. So what we'll do here is, in our case, we are getting that infinity case or 0 by 0 case. So we have to elevate that problem. So we are taking limit. This help of this theorem with limit r tends to 0 and the function is 1 by r del t del r. So you can say that the first function, this is gx, this is gx, g of r, and this function is f of r. And you can write like limit x r tends to 0, and you can write it like del r del t del r and del r del r r. Okay, so this is a this goes here, and r is another function. Okay, 1 by r is not fr. Let me correct that. So what I mean to say is that this uh, uh, let me write like this, the same thing. So this is f of r. So del r. So this gives you equals to del 2t del r2, and this is 1. So finally this particular land up to del 2t del r2. Okay, so it is equivalent to say that 1 by r. So 1 by r del t del r is equivalent to say that del 2t del r2. Okay, and now we substitute this in equation. So substitute above in governing equation, sorry, and we get del 2t del r2 plus 1 by r del t del r is equals to 0. So del 2t del r2 plus del 2t del r2 is equals to 0. So essentially you get 2 del 2t del r2 is equals to 0. And since 2 this thing is 0, 2 2 if goes here, then you simply get del 2t del r2 is equals to 0. So now this is the proper boundary condition. This is the proper boundary condition at this is the appropriate create boundary condition at r is equals to 0. Okay, so r is equals to 0. So here this is r is equals to 0, suppose. So we are having 1, 2, 3, and like that. We have this is r is equals to capital R. So suppose I write I for this one and I plus 1 for this one. And if I take the point below R, I can write it as I minus 1. Okay. And this distance is delta R. And delta R remains same. Everywhere delta R is constant. Okay. Now I want to discretize this. So delta d del 2 t del R2 has to be discretized at I. I is nothing now, a boundary point. I is equals to 0. And if you are starting with 1, 2 like that, this is 1, this is 2, like that we are starting, and this is n plus 1, and this is n. We are starting like that. And so this becomes 0. Okay. For del 2 t del R2, which method you will use? Central in space. Okay. So using central in space, what value you will get? Ui minus 1 minus twice ti plus ti plus 1 delta r square is equals to 0. Okay. So what you can write is ti minus 1 minus 2 ti plus ti plus 1 equals to 0. And all these are at n plus 1. All these are at n plus 1. Boundary conditions are always at n plus 1. Now, I minus 1, this value at this point, and at this point should be same, isn't it? Because whatever the variation in this direction, whatever the variation is there in this direction, that also should be same in this direction, because there is a theta symmetry. In theta direction, there is no change. So if you go right or if you go left, the values will be same. So what I can say is that because of symmetry, we can say symmetry ti minus 1 will be equals to ti plus 1. And you can substitute in this above equation, and you can write minus 2 ti n plus 1 plus 2 ti plus 1 n plus 1 equals to 0. And now you can take 2 outside, and you can write ti plus 1 minus ti n plus 1 equals to 0. And since this has to be 0, so ti minus 1 n plus 1 minus ti plus 1, ti n plus 1 will be equals to 0. This is the equation. Now, from this equation, you have to find out what is your Ri. Ri means R1. R1 is, we are starting from 1. I is 1. R1 will be equals to what? Ti n plus 1 minus ti minus 1 I plus 1 n plus 1, that is R1. And what is central coefficient? A1 will be equals to, what is the central coefficient? Minus 1. So we got R values and A coefficients. We can use Gauss-Seidel method, and we can solve this problem, isn't it? So solution algorithm, if you have to write for this particular problem, you can simply write, uh, okay, solution. I'm writing in a very brief manner, but if it is, you have to write in that sense, you should write with complete equations. Okay. So first thing we usually do is initialization. We do initialization. If there are initial conditions or your arrays, these need to be initialized. And then you start with outer loop. You, even though this problem is not unsteady, you solve it as a unsteady problem using false transient approach. So you have an outer loop, that is your do loop, and then within that, then you have an inner loop, and then again you can start do, and then interior points for I is equals to 2 to n, you find out ri, ai, and then you find out t new I is equals to ti old plus omega ri a. Using this equation, then you go for boundary conditions. So boundary conditions for I is equals to 1, you find out R1, A1, and then you find out T1 new plus is equals to T1 old plus omega R1, A1. Similarly, for I is equals to n plus 1, you find out Rn plus 1, then you find out an plus 1, and then you find out t n plus 1 new is equals to t n plus 1 old plus omega r n plus 1 divided by a n plus 1. Once you have found out, you have a updation and while condition and all like that. Okay, so while you have first while RRMS is greater than some small number. Then once this is done, you will update the loop. I think I do not have space in the bottom, so I'll just go here in the right hand side. So so you update, sorry for this, you update n is equals to n plus 1, and then so that is nothing but t old is equals to t new. You do it appropriately, okay? Don't think that what I said and then like that. While you have these conditions, t new minus t old magnitude greater than some epsilon, and then third thing you will have to do, print the values of t I new. Okay, that's the algorithm you generally follow for the. How much time do I have? How much time do we have?
Sir, time is over, sir.
Time is up. Only just I will give you homework. What you have to do is you have to do the same procedure for unsteady problem. Okay. So unsteady problem I am just writing here, del del 2r del r square plus 1d del t del r. Uh, with initial conditions at t is equals to 0, t is equals to some t naught, given t naught, and boundary conditions at r is equals to, say I'm now writing n plus 1 del t del r is equals to 0 insulation, and at r is equals to 1 del t del r is equals to 0. Okay, so show interior. So the question is show interior boundary discretizations, discretizations, and an algorithm. Okay, do this. Okay, thank you.
Sir, sir,
Yes.
I have a doubt.
Hmm.
So in steady problems, why we are taking the difference between T new and T old?
That is a forward difference we are taking in time.
No, so we are already checking the residual, right? R less than epsilon.
Ha.
So
But if you have a derivative term, suppose if you are solving an unsteady problem, then you have a derivative term, right?
so no, I'm talking about steady problem, like
Ha. In steady
Laplace.
problems, ha.
In that last class, you said in the algorithm, first we have to check the RMS of residual, and then the RMS of difference of T new and T old.
Ha.
So I think that
So I got it. I think you have a problem with this. So what we are doing is, suppose what we are saying is, now we want to solve steady problem. Okay. So steady means I want uh, all steady state values at all these points, boundary points as well as interior points. Okay.
yes,
Okay. I want values at all these points. Okay. Now, in case of uh, the explicit method, again you can calculate the values at all these points, and then you have to get the steady state value. Okay, like that. In implicit also, you assume some values here, guesses. You understand?
yes, sir.
Guess value is required. Guess. So suppose there is a guess value. So this guess is acting like an initial condition. Now I want to improve this guess. So I will move to some next level where I will calculate the new values of the all the points. You understand?
Yes, sir.
What is the new value at this point? That I will calculate. So this guess, I will keep on correcting this guess. Okay. Whatever the guess was there, now it comes this solution. Okay. Now then I'll go to another one. Are you with me?
Yes, sir.
Then I'll go with another one, and then again I will calculate uh, at all these points. Okay. This arrow means okay. Now while moving, uh, now shall I go to another one also? Shall I go to another one
No,
also? Why
no,
no? Why no?
that
Only
depends
three?
upon.
Now we have to check.
Yeah.
Whenever I'm correcting my guess, suppose this is a X guess, I have corrected this guess and I got now this new guess. Now with this new guess, I got another new solution, guess solution. So is this guess solution I obtained is a correct solution or not? Or is a steady state solution or not? How will change? When there is no variation from this iteration to this iteration, isn't it?
Yes, sir.
So that is the reason we have to check. So whatever the guess values you got, xg double prime, whether these values and previous guess values are smaller or not. So this should be less than or equal to 10 to the power minus 4 or minus 5, like that. Then we say that it is equivalent to 0. So if there is no change, then we will say stop. Our steady state means we want such a value where there is no change between two iterations, present iteration and previous iteration. That is steady state. So this is like moving in time. We are doing in calculation in space, but we are moving in time. You got it?
Yes, I understand, but what I'm saying is that the difference between the last iteration and new iteration will be same as the residual, right? We are already checking the residual.
No, residual is different. Residual is what I'm saying. What we are doing is, suppose we are calculating interior points. Now, say, suppose you are at this level. I'm calculating this point values, and this point values. In that case, we are taking this gauge value. Say, suppose this gauge value is taken here. Then we are itself calculating some proper values at this location. Okay.
Okay.
These values will be at x prime g values will be those values for which residual will fall. Okay.
Okay.
Residual will be falling. Okay. It doesn't mean that for all these points residual is 0. Doesn't mean that this also have a residual 0.
So for unsteady problems, it's okay, but for steady problems,
Steady problems, how will solve then steady problems? This is called as false transient approach. We move in time and then we keep on checking. This is called as iteration. There we will say time stepping. This is now iteration, first iteration. In first iteration, we guess the value and find out the appropriate values. Then we do next iteration and we find out another appropriate values. But within that iteration itself, we have to find out all the interior points and boundary points such a way that residual of that corresponding equation falls to 0. So you will say that here everywhere Rg prime is also 0, sir. So I should stop here. No, Rg prime and Rg, this will not be 0. It is possible. So we want such a case where xg prime and xg double prime and xg, I mean present iteration and previous iteration values should be 0. We have to proceed in iteration, forward in iteration. So it is like a transient approach. It is like you are moving in time and going towards steady state. That is the meaning of false transient. Are you appreciating this?
So in Laplace, we are not taking that del t by del t.
In which lab?
So Laplace, when we are applying false transient approach, we are not taking del t by del
In
t.
which lab? In which problem?
Uh,
Because I have not till now given any false transient kind of problem.
no, sir, I'm just in that second assignment, computer assignment.
Computer assignment. That is not a lab. Computer. I thought lab you are talking means energy lab.
No.
Computational lab.
So in false transient approach,
Second problem you will have to solve like this only. False transient approach only.
Yeah.
Because it's a Poisson equation. There is no time derivative.
Yeah, there's no time derivative.
Yeah, but you have to do iterations. From first iteration, you have to go to second iteration. So that is iteration loop is outer iteration. And within every iteration, within every outer iteration, there is a local iteration loop. That is called an inner iteration. That is what I am saying. Inner iteration means wherever interior points residual should fall, and boundary points residual also should fall.
So when residual less than epsilon, then we are not changing time, right?
We should stop. We should stop and print the latest values. This is the condition, na? That is the condition.
Yes, sir.
If you are checking with previous value, present value are not varying with respect to previous values, you stop and print these values. These values will be your steady state values.
Yeah, but sir, in last class you said first we have to check.
I did not say anything else. If you might have understood like that.
Yeah, so first while loop we are checking the RMS of residual, and in the next residual, next loop, we are checking
Anujit,
that.
you are
Yeah,
confusing. First is the outer loop.
yeah.
There is a outer loop. Outer loop, uh, you will enter in outer loop. So I entered in outer loop, for example. Now, in outer loop, there will be inner loop. So
Yeah.
for this inner loop, you will have to check first RMS. That is what I am saying. RMS should fall.
Yes.
Once RMS is fall, then we say that what are the values we obtained for this whole domain? These are xg prime values.
Okay.
Then we move to next, this xg for calculation of xg double prime.
So in that,
In that case, when to stop this outer loop? So here we will say while outer loop should be stopped while xg double prime minus xg prime magnitude is greater than epsilon. Why greater than epsilon? Because this is the true condition. True condition is there. So okay, go do this. This is a do while.
yeah.
Yeah, that is the reason we have to say greater than, not less than. So something has to be related to program. Are you getting this or not?
So for unsteady, it's okay, but for steady,
For steady also, this is a iteration loop, na?
yeah.
Eh,
So if if the residual condition is satisfied
Where?
in the second loop,
In the second loop, if residual is falling zero,
zero,
it will then if,
then the
then it means
like
that all the xg prime values you got, these are correct values. Correct
yeah,
values for that iteration.
okay.
Okay. Now you have to check whether you
So
have reached steady
for the
state
next
or not. Next iteration.
for the
Shall you
next
move to next
iteration, but
iteration or not?
the values are
You have
not changing, right?
No, it will change. They will change. For next iteration, this will become guess values. Xg prime
Yeah.
values will become guess values. With these guess values, you will calculate this again new values.
But the residue will be already less
No,
than epsilon.
here,
Yeah. If we go again, but the
here first you are not checking residual condition, na? While
yeah.
RMS is
Yeah.
this thing, then you'll enter here. See here, RMS is now RMS is 0, suppose here. Now we entered here. Now what
Yes.
is there any condition checking for RMS? No.
No.
If
No.
you will
No.
enter inside the loop,
Yeah.
you will calculate all these values. But when you calculate these values, now RMS is 0. Again RMS will be, you will get in a print, now here, not here, as a output, RMS will be 0 here. So
Yes.
you are still again going in another this thing, so you enter in this. There is no check here. Ki RMS 0 hai, so I cannot go here. Okay,
Yes.
that is do while loop. If you are while, then problem.
Yeah.
Next while, then problem. You'll have to make your logic like that or programming like that, such a way that you should be in a position to enter. Means whatever I'm saying, this as a kind of imagination. First, imagine this. Then programming is changing of while loop here and there. Okay. So my intention is not to give you more focus on this. Just it's a pseudo code.
Yeah.
But understanding of this, if you understand this procedure, what you are doing, then you can program it well. And programming can vary from person to person. But as you pointed out now your problem, then you should not write while loop here. Then you should have something so that you can go inside that loop at least. Otherwise,
Yeah.
you will not never be able to enter. Yeah. So check those things. Okay. Check those things.
Okay, sir.